A light inextensible string supports a block of mass m. The block moving a horizontal circle of a radius r with constant speed, while the string makes a constant angle with the vertical. The time taken for the block to complete one full revolution is t. Part A. 1. Draw the free body diagram of the block when it's at the rightmost point of the circular path. 2. Express the tangential speed of the block during its uniform circular motion, expressed only in terms of r, t, and physical constants. 3. Write the expression for the centripetal force acting on the block, expressed only in terms of m, theta, and physical constants. 4. Under the same initial conditions, write the expression for the centripetal acceleration of the block, expressed only in terms of theta and physical constants. Alright, part 1. Draw the free body diagram at the rightmost point of the circle, so it's at this position. Obviously, there's gravitational force, Fg, and the tension force that is pointing towards the direction of the rope, Ft. So that's it. That's the answer for part 1. Part 2. Express the tangential speed of the block during its uniform circular motion. From the question, we already know that the time taken for the block to complete one full revolution is t. So we can obviously get the angular speed, which is 2 pi over t. Because, one revolution is just one circle, right? And this is like the angle of it is just 2 pi. And how do we convert the angular speed to the linear speed or tangent speed? We just multiply it by the radius in AP1. So we will get, after we combine them, we'll get 2 pi r over t. That's the answer. For second part. For the third part. Oh, look at the stuff in the parentheses. Expressed only in m or theta. There's no t involved, so which means we cannot just use mv squared over r, because we cannot involve velocity to the expression. So how do we find it? Well, don't worry. Since the ft is pointing that way, right? And there's also gravitational force. Alright, let me ask you a very important question. Since the block is moving in a horizontal circle, is it moving up or down relative to this circle or the surface it is rotating on? Obviously no, right? So vertically, the object is at equilibrium. Let's separate them to components. From the analysis we did before, we can get that the vertical components are equal. And the angle, this is theta. So since the vertical components are equal, we can just write the expression of ft times is it cosine theta is equal to fg. And which we can get ft is equal to fg over cosine theta. And now it's asking the centripetal force, right? What is centripetal force? It's just the sum of the force, or the combination of the force that pointing towards the center that is rotating with. Center of the circle that it is rotating on. So in this situation, the centripetal force will just be this component over here. What is this component? Obviously, it's just ft times sine theta, right? Oh, it's supposed to be your answer, but over here we cannot use ft because ft is just a value that we give it when we're doing the analysis. What is ft? Fg over cosine theta. So what we should do is plug ft is equal to fg cosine theta over cosine theta to ft times sine theta. Oh, by the way, I should write this is equal to fc. After we plug it in, we'll get fc is equal to fg times sine theta. over cosine theta, which will be mg times sine theta over cosine theta. What do you realize? What do you realize? What is sine theta over cosine theta? Oh my, isn't that tangent theta times tangent theta? So that is your expression for the centripetal force. Let's check it again. It says express it only in terms of m, theta, and physical constant. What's in our expression? M, theta. These are the two variables we can use. What is g? Oh, g is just physical constant with value of 9.8, negative 9.8. I'll just put 9.8 here. And tangent is just weight of math. It's just a method of math. So it's totally fine. Now, part 4. Under the same initial conditions, write the expression for the centripetal acceleration of the block. Express it only in terms of theta. So now, from part 3, we already know that the centripetal force is equal to, what is that? mg tangent theta. Right? And using the Newton's second law, m times ac, right? F equals ma. Oh my, let's cancel m. So the only thing left is ac will be equal to g tangent theta. Oh my god. No mass involved at all. Isn't that surprising? But let's still check it. Check to the requirement of the questions. Express only in terms of theta. Yeah, only theta and physical constant. Only g and tangent. Alright, that's the right answer, 100%. Let's keep going to part B. Alright, part B. As you can see, I completely replaced part B because the original one wasn't good at all. It basically just repeated what we just done in part A. I'm really sorry about that. However, I assure you that the brand new Part B now fully justifies its position and role as Part B. So, Part B. Assume the length of the string is L. If the length of the string becomes twice its original value, other variables remains the same. Determine whether the new linear speed of the object would increase, decrease, or remains the same. So for this type of question, you have to build a mindset that, like, you first needed to identify which physical quantities formula involves the variable you want to find. For example, in this question will be v, the velocity, and then you'll try to find another expression for it, for the that physical quantity, and then combine these two equations or formulas or expressions together. You can solve for the expressions of the variable. And now let's see which formulas actually involves v, the velocity. So if you remember the formula for the centripetal force Fc, it is actually equal to m times v squared over r. And if you remember what we do previously in the third part over here, in part 3, in part A, the centripetal force can be also written as an expression of mg tangent theta. Right? And we're trying to solve for v. And after we simplify it, we can get v is equal to the square root of rg tangent theta. And now some of you may just stop here and says, oh, it would not be affected because this expression only involves r, g, and theta, and it's not involved by L. You may just stop there and laugh. Oh my, it's so easy, but actually you're wrong. You're wrong, kid. Alright, now look at the graph carefully. This is L, right? And this is a radius. How do we write the expression for radius using L? When you connect this part together, it's now basically a triangle, right? Triangle. Using trig, we can write the expression that r is equal to L times sine theta. Oh my. As you can see, there's actually a relationship between L and R. When one is increasing and the other one is also increasing, we can just write when the L is increasing, R will also increasing. So now in the question, it told you that when the string length is twice its original value, what it's actually telling you is that the radius is actually twice of its value, because when the L becomes 2L, the R, if want the equation to be equal, the R will actually be 2R. So let's write down our new expression. V new is actually equal to 2R times G times tangent theta. So it's actually increasing because relative to the velocity before, it's like multiply it by 2 inside the square root. So it's actually increasing. So increase is your answer.